Therefore, before coming to this time, I little bit to check the previous proceedings and the document in order to get some idea of this meeting. Yeah, it is very difficult to understand diverse subject in mathematics. But anyhow, in my understanding, this members of this community endeavors to find useful information, universal properties in various geometry for general to something forms. And for this purpose, probably mathematics is a good tool to study that because math itself is a universal tool and rigorous. On the other hand, my approach is based on thermodynamics. It's quite different. Thermodynamics is not a mathematical subject. It is stated in more descriptive ways, something like that. And it is impossible to convert heat completely to work, something like this. In spite of this, thermodynamics is exact science. It's hold every area from elemental particle to astrophysical object like black holes. So I hope that my talk gives some framework of understanding of geometry from such a universal viewpoint of physics. Uh, since thermodynamics was established more than 1 century, you may think that it is out of current research, but it is not true. Even right now, many important discussion has been made has been made in front of research. Uh, Presently, the standard understanding of entropy is that entropy is a measure of disorder. However, when we look inside various material, the notion of disorder order becomes ambiguous. Difference between randomness and order becomes ambiguous. Complexity, simplicity is also ambiguous. And this is particularly true when information is connected to this entropy. Can you say whether the number pi 3.14 something is random number or ordered number? It's difficult to. And in a deep sense, this conceptual difficulty is related to the fundamental and long-standing problem in some dynamics. That is the third law problem and hysteresis. And among them, the essential problem is which state variables. This confusing situation can be seen when we look into the literature of biology. In this famous book of Schrodinger, he described living systems as periodic crystal. what is the meaning of this? And in this textbook, living systems are ordered, but not simple as crystal are. What is the meaning? Is it true? This is the subject of my talk. So first, I describe the origin of problem. What is the order? Uh, I have been long studying glass physics, and actually, so in a category, I'm in material science, and I live in solid state physics. There, um, order means perfect periodicity. Perfect uh, perfect crystal has perfect periodicity. Periodicity means order. So uh, any defect, imperfection in crystal is regarded as disorder. For studying periodicity, students have to learn many mathematical tools of symmetry property like space groups and so on. However, material science is developed. We encountered those material whose structure is ambiguous. Good example is quasicrystals. The structure cannot be classified any of 230 space group. Obviously, a living system, we cannot find periodicity, but we cannot say that these systems are disordered system. It must be something ordered state. Uh, I have been long studying glass properties. Uh, Generally, glass are regarded as fully disordered system, but it has something order. Here shows a snapshot of atom arrangement in molecular dynamics simulation. Uh, can you say which is the liquid state and which is glass state? It's very difficult. In spite of this, there is a distinction between liquid and glass. Glass transition is identified by observing a jump step in specific heat as a function of temperature. What is the step of this specific heat? Normally, specific heat has two contributions of phonons and thermal expansion. But actually, it is clarified that these two contributions have only a negligible contribution to this step. Therefore, another additional contribution, which is called configurations contribution, should be considered. This quantity component is determined by something variables we call order parameter. What is the order parameter for disorder system? Uh, Nobody understand until this time. A lot of model theory have been proposed, but yet there is no consensus. This conceptual difficulty is related to the problem of third law of thermodynamics. as you know, third law claims that the entropy of any material vanishes as approaching zero temperature. Uh, Formally, everybody can accept this law. However, in practice, we find that there are a lot of exceptions for this law. Rats defect, random alloys, glasses, all have non-zero entropy at zero temperature, which is called residual entropy. These crystals have a lot of various atom configurations, which create configuration entropy. This configuration entropy is the source of residual entropy. Then, how to understand this exception? Uh, Conventional excuse for presence of this exception is that these defect states are non-equilibrium states. And if we wait for a long time, this may be uh, changed to perfect crystal order state. Is it true? Uh, this conventional excuse contradict thermodynamic principle. Uh, if free energy of crystal is plotted as a function of defect concentration, we find minimum point. This corresponds to equilibrium concentration. Therefore, perfect crystal is rather unstable. It is not permit. And furthermore, in reality, we never see the establishment of equilibrium concentration in equilibrium in crystal, in solid. The concentration of defect is determined by preparation condition. And once the crystal is formed, then this number concentration cannot be changed. So it is temperature independent. It's a frozen state. Another problem is hysteresis. Glass is traditionally regarded as a non-equilibrium state. The main reason of this is its history dependence. A basic idea of equilibrium in thermodynamics is that once equilibrium is established, then current properties are independent of previous history and determined by state variables solely. Uh, so this contradict what this is a basic understanding, our understanding. However, if we closely observe, then we'll find that hysteresis is a common property of any crystal. Metals have dependence of previous thermal history, for example, annealing and others. And memory materials, by construction, the current state is determined by previous history. Silicon crystal has also preparation dependence of preparation conditions. So if we consider that only temperature and pressure are state variables, it's eventually reach a sort of conclusion that all solids must be in non-equilibrium states. It's a serious problem. By knowing this serious problem, Bridgman advised not to conclude that the law of thermodynamics do not apply to our system if at first we are unsuccessful in finding a set of parameters, that means the state variables that determine an energy function. Instead, he suggests that we have not a complete list of state variables. Uh, Unfortunately, until recently, we don't have a complete list of state variables. Okay? えっと、So, fundamental problem is which is state variables. For gas, it's certain that internal energy is a function of T and P only. But there is no proof that it is true for solid. Okay. Then, when we investigate which state variables, we have to know the definition of state variables. You can say that state variables are defined in equilibrium. Then, we should ask what is the equilibrium? Answer is equilibrium is specified by state variables. In this way, we follow in circular argument, something like a chicken and egg problem. We cannot escape from this dilemma. It's a big problem. Uh, However, very recently, fortunately, this dilemma has been solved by Giftopoulos and Beret to eliminate this fundamental dilemma. We have to get out the equilibrium world. And by starting general situation of equilibrium, we investigate what condition is required to reach equilibrium. We observe that non-equilibrium state always is accompanied with energy flow. And by inserting an appropriate device, we can extract work from this energy flow. Once equilibrium is reached, established, then we cannot extract work anymore. So in this way, we can define equilibrium state as it is impossible to extract work from equilibrium without impacting environment. So we don't need to use word of state variables. By defining equilibrium in this way, the second law of thermodynamics is stated as for a fixed energy and fixed constraint, the isolated system has one and only one stable equilibrium state. Actually, there are many different ways of expressing second law. This way of statement is the latest one, so maybe you are not familiar with this statement. However, if equilibrium state is read as the maximum entropy state, then you can reasonably understand this statement as the state of system is changed until reaching maximum entropy state. Okay. And another feature of this statement is that uh, for each constraint, equilibrium state exists. So there are many equilibrium states as a number of constraints. Okay. What is a constraint? In macroscopic system, constraint mean wall, rigid wall. It's obvious. But in microscopic world, the substance of constraint is wall. Macroscopic wall can be regarded as energy barrier with infinite height. In solid, the substances that inhibit atoms from moving beyond the unit cell is energy barrier. Okay. Then we are able to define state variables. For gas, volume is state variables. In microscopically, the boundary of gas is always fluctuating, but the time average defines volume. So in this way, we can define state variables as the time average of dynamical variables, provided the value converges uniquely. So important thing about state variable is time invariance against fluctuation and unique value. For example, for gas, atom change their positions, always change position, and average of atom position is indeterminate. Therefore, atom position cannot be state values for gas. But for solid, it has different value. It's always atom uh, position is fluctuate to around the equilibrium position. Therefore, equilibrium position is the time average and can be qualified as state variables. This conclusion is fully compatible with our observation. For gas, atom position has no correlation to the internal energy, so it must not be state variable. But for solid, if we displace one atom into interstitial position, obviously energy is changed. So, and interstitial positions are equilibrium position. Therefore, energy is a function of equilibrium position. That means the state space in solid is spanned by a lot of variables and atoms dimension. This is a very important consequence, important conclusion of this study. Uh, and this time invariance or invariance against the fluctuation can be shared with the idea of order parameter. Order parameter is introduced when we consider a phase transition. Good example is ferromagnetic transition. Below Curie temperature, magnetization appear, and this quantity is regarded as order parameter. Microscopically, local moment has time fluctuation. However, by taking time average, it has non-Bunsen value. Above Curie temperature, this magnetization and order parameter vanish. But still, each atom has local moment, but the orientation of this local moment is randomly distributed. Then time average gives zero value. So order means invariance against thermal fluctuation. And furthermore, this can be generalized to information. Information becomes meaningful when always the same answer is received, whenever it is measured. Uh, Example, this is the time map of my home. There is no regularity, no periodicity. Yet each atom is assigned with a unique address. Then postman can deliver postal material without error because the time map is the same yesterday, today, tomorrow. If some reasons repeat moving out and moving in, then and if a time map is not updated, then postman is confused. So the time invariance is an important ingredient of information. Language is the same. For Japanese, alphabet has no meaning. So any English text is merely just random array of alphabet. However, the word apple is used to refer to concrete physical object of apple. Then we can recognize that apple really means apple. If someone misuse this word, then we Japanese are confused with that. So the time invariance is the most important ingredient for state variables. えっthe last topic is information cost and relation to the configuration entropy. えっと、the physical property of water is independent of the height at which measurement is performed. Energy is a function of T and V only. But there is a case in which the height plays a role. Look at hydraulic power generation, and, and the height difference in height is the almost only variables which we are interested. How to treat that? Uh, when two waters at high and low elevations are separated by constraint, I mean wall, then they cannot interact each other, and we don't need to consider the difference in height. In this case, this variable h is regarded as inactive. Call it frozen coordinate. So this variable is irrelevant to the property in the present scope. It is frozen coordinate. However, once we remove constraint, then and this frozen coordinate come to play. These two water cannot be independent. It's interact each other, and upper water fall to lower place. In crystal, defect has many atom configuration, which create a configuration entropy. Uh, However, uh, one specific sample of crystal can have only one configuration. And this configuration is separate from other configuration by energy barriers. So present property are independent of other configuration. Therefore, the entropy of this particular sample uh, is zero at zero temperature. Therefore, in this way, the third law is recovered. うん。Okay. This has a significant consequence of information theory. Yeah, it is somebody, yeah, this also describe the regularity or order cannot serve to store the large amount of information required by living systems. But actually, this is not true. Uh, Look at silicon. Silicon has only a unique structure of diamond structure. In this sense, it is simple, and entropy is zero. However, uh, computer industry create a lot of uh, various devices from only this single chip. And furthermore, a single chip of 1 GB memory has 1 GB different memory states. These different states must be equilibrium state. Otherwise, recorded memory can immediately lost. Therefore, these are uh, these configuration equilibrium state and realization of different configuration is possible simply because energy of crystal is determined by equilibrium position. And finally, uh, to maybe there is no time. So I just mentioned that information is brought about by configuration entropy. However, this can be achieved without paying a cost. Somebody, Kaufman, claims that evolution biology as order for free, but it's not free. We must pay energy cost because equilibrium state cannot be changed without working this system. So I reach conclusion. I have shown that order constraints, state variables, structure, information, uh, all these notions are kind of thought synonymous in some dynamic context. They have common property of invariance against fluctuation and unique for one particular equilibrium state. Uh, this is a famous picture, and this is a very boring picture. But in some dynamic context, these two pictures have the same value because of it is unique. Unique. So sound dynamics cannot evaluate the value of a picture. And geometry is described by of solid is described by equilibrium position. So every atom is playing zero. And the information of solid is not usable for free. Okay, thank you. These are described in various papers, but I suggest the last one because of a review paper. Sorry, thank you. Okay.
Yeah, thank you very much. Very interesting talk. So, I read number three, I think. So,
Mm.
about the order of glass parameters in foundations that was published last week. So I found it very interesting, and I think these ideas should also be applicable to, let's say, life systems and DNA, because their life itself is working only in certain conditions. For example, a frog jumps only between 5 degrees and 25 degrees, and otherwise it does not jump. So these constraints for living organisms are very important. So thank you very much. Anyway, so questions from the audience. Pino, you're as a physicist.
Since you are, I have very much appreciated the last remark in which you have put together the Leonardo's picture and a very elemental drawing, and say that entropy, thermodynamics cannot appreciate the fine art, and that's a very, very deep point of view. I have expressed also this point of view in my lecture on thermodynamics, a book which has been published some years ago, in which I was trying to express what is order, and which has not an absolute meaning, but is more referred to an interpretation key. When one has the key to understand the meaning, also it can define order in a more general sense.